Okay, you're live.
Okay, so hi everyone. Good morning, good afternoon, and good evening, depending on the time zone. This is Daniel, and this is the Linux Foundation's Decentralized Trust Learning Group on Zero Knowledge and SNARK application development. So this is like a pretty simple learning group. We cover, or we have been covering practically different topics on zero knowledge proofs and SNARK, mostly from an application development perspective throughout the year. And this is kind of well, I would say like not too formal learning group on this topic. So let me start briefly with the logistics of this learning group. It looks that way that we just managed to organize one meetup throughout this year. Practically, it was almost the third Thursday of each month. We started from 6 o'clock in the afternoon, Central European time. That's like 9 o'clock Pacific, and I don't know, I think like 1 o'clock East. So I'm not quite sure at the moment due to the this time changing chaos practically, but I mean that's more or less the plan, or that was more or less this plan. Uh, the logistics looks that way. We got like 1 hour practical presentation that was from myself. I introduced different topics on zero knowledge proof and ZK, mostly from a programmer and application developer perspective with some theory. So basically, I'm not a mathematician myself, and well, sometimes I try to, yeah, I would say go in depth into the mathematical theory, but basically I focused mostly on a application developers or programmers perspective of the topic. It looks that way that basically things are organized on meetup.com. So practically you find all the previous and subsequent meetups as well on meetup.com under Linux Foundation Decentralized Trust. Basically, I mean, the link is here for Hungary, but anyway, you find it overall. So this is a non-location specific zero knowledge learning group. So it's just, I got like more admin right on the Hungarian event side. Uh, well, actually, as these sessions are pretty limited, I mean, in time, in terms of the possible discussion, we got basically like a Discord channel for things to organize and for discussion. So practically, if you're on Discord from Linux Foundation Decentralized Trust, you're gonna find us under community, and the last like subchapter of community is the zero knowledge learning group. And then, well, I would have encourage everybody for that the discussion should be done or carried out here, because again, I just try to keep these meetups to limit it to 1 hour each month. So we might have some limited time for an in-depth discussion. But if you have any questions, any comments, or anything that you're interested in, just feel free to chat and drop us some line here in the Zero Knowledge Working Group in the Linux Foundation Decentralized Trust Discord channel. If you're not on the Discord channel, just Google it, and then you get an invitation. Just Google LFDT Linux Foundation Decentralized Trust Discord, and you're gonna find like an invitation right at the first match or second match, or probably pretty fast. Okay, so that's logistics. And we have a GitHub repository as well. So basically, it's like under LFDT, Linux Foundation Decentralized Trust Labs, and we got a ZK learning group. Practically, it's a repository for just collecting all of the knowledge that were covered here. So practically, we got here like all of the presentations. Most presentations, I think all presentations have like a recording. So you're gonna find the recording, you're gonna find the slideshow, you're gonna find actually a link to the meetup. Sometimes there's like quiz and links and literatures or developer challenge. So practically you're gonna find everything here. And then you will find like demonstration code here as well, like for instance, under Circum and Noir. So practically everything is here. And then, so for the logistics, this was like the plan throughout this year. We started in February with some theory, continued with like polynomial commitments, interactive oracle proofs. Then we focused on programming. We just covered two different zero knowledge development frameworks, Circum and Noir. And then from September, we focused on like different applications, focused on like free stuffs like proof of reserve and proof of solvency systems. October, there was one session on zero knowledge machine learning, which is like a little bit like hyped, I would say, but it's due to the fact that it's like, machine learning. And I would say AI is pretty much hyped at the moment. And in November, I mean, in this session, we focus on rollups, and then probably in December, I'm gonna have one short meetup as wrapping up the whole year. But the good news is that the plan that we are continuing this zero knowledge learning group next year as well. I'm sure I have a few topics like, for instance, STARKs or lookup tables from the theoretical perspective. Probably we're gonna cover one more zero knowledge programming framework. I'm still not sure which one, and sure we can have like other application areas as well, like zero knowledge logins. I'm still brainstorming on the exact thematic for next year. So if anybody has like any ideas which topics should be covered like next year, or if you have like any special topics that you're interested in terms of zero knowledge or programming theory or applications, just feel free to drop some line here in the chat, and then yeah, I mean, I will figure out. We're gonna try to invite some other speakers as well, so it's gonna be, or hopefully it's gonna be not so boring that I mean, that you just always hear my voice. Anyway, so let me start with the today's session, and that's like the agenda. I got like one slide on zero knowledge proofs as usual. Then this is not gonna be like a very much deep theoretical presentation, rather on a high level. So basically, I'm covering blockchain scaling. Then I'm just introducing the different rollups. It's like optimistic rollups and ZK rollups, and some differences and similarities or advantage and disadvantages on optimistic and zero knowledge rollups. Then we're gonna cover a little bit like how a ZK rollup can be implemented, like how like an off-chain transaction with like Patricia or sparse Merkle tree looks like, how a rollup looks like, and how like a real ZK rollup on a high level should work. And then at the end, I have like one slide on like a special niche area, which is like naysayer proofs and rollups. And of course, as usual, I got like one slide on a challenge, some links and resources, sorry. And if we have some time, there's a Q&A at the end. So that's the plan for today. That's the agenda. And I would say, let me start with the presentation. So as usual, this is my one slide introduction to zero knowledge proofs. It's practically, I would say, it's a game between like two parties. We got, of course, Alice, or we can call it prover, and there's like Bob. We can call Bob as a verifier. And then basically Alice proves something. Alice proves, or the prover proves, that she knows the fact. And Bob, I mean, in a cryptographic sense, and Bob will be, or the verifier will be sure that Alice really knows this fact. And then it might be possible without revealing this fact by Alice. So it might happen that the fact will be known only by Alice, but despite Bob gonna trust Alice that she really knows this fact. It's like one example is like proving that I know like the preimage of a hash function, and practically I can do it with like zero knowledge proof. I can prove that fact that I know a preimage of a hash function without actually revealing the preimage of my hash function. That's possible. And that's like, a sequence of communication, or if we speak of SNARK, we actually like one round communication, because if there's like too many communications, then it's just difficult to verify it in a smart contract or in blockchain. And from a general perspective, or a little bit like more formal perspective, basically we can express many different things as a zero-knowledge proof. It's like hash function was one idea. It's like, where's Waldo, like similar games are other examples. But basically, we speak of usually like general purpose zero-knowledge platforms. So in general purpose zero-knowledge platforms, there's a possibility to implement a domain problem somehow by developers or cryptographers, and basically to develop like a general purpose or a general problem. We usually have a computation model, and this computation model is pretty specific. That's a so-called arithmetic circuit. So in an arithmetic circuit, in a little bit more formal way, we get a circuit. It has some public inputs. Usually it has private inputs or witnesses. And then basically, I mean, the programming flow looks that way, that usually we define our program in a little bit higher level than pure arithmetic circuit. Then we compile to arithmetic circuit. And from arithmetic circuit, I mean, that's kind of an intermediate representation, I would say. But the point is, for arithmetic circuits, it's just it's pretty easy to compile or calculate polynomials, and basically eventual or polynomials are gonna give us the zero-knowledge properties, or the properties that we need for this proving and verification algorithms and stuffs. Being more formal, we got like two algorithms. We got the prover and we got the verifier. Practically, the prover gonna take the public input and the private input and creates a proof. There's a kind of a preprocessing argument as well, but it's not so important for the first one, I would say. And we got a verifier algorithm, and the verifier gonna take like the public input and the proof and some preprocessed argument as well. And the verifier either accepts or rejects that proof. So again, important to note, we got here just the public input and the proof. So practically, the verifier does not see the private input. And we got a few properties that are pretty cool, I would say. First, our proof is small and easy to verify. That's like succinct. We got some other cool properties as well, like complete and knowledge sound. Complete means that basically, if there's a proof, then basically I mean, if like Alice really knows a fact, then she can create a proof that Bob gonna accept. And then a knowledge sound is the other direction. So if Bob practically accepts like a proof, then Alice really knows practically a fact. And then based on that fact, this proof was generated. So that's like the two meaningful properties in both directions. And of course, we got one property which is actually optional, which is zero knowledge. Zero knowledge means that basically Alice won't reveal the private input. Okay. Well, actually, the whole stuff makes sense without zero knowledge as well, because the point is that the proof is like small, which is succinct. So basically, small in size and easy to verify or fast to verify. So we might as well use this whole structure in a sense that we are not going to hide any private input. We just want to somehow use the system for proving that a complex computation was executed in a correct way. Okay, so that's like one slide summary of zero-knowledge proof. And let's just start with scaling and blockchain and rollups. So why do we need rollups for the first round? So let me just start with blockchain scaling. So the problem is that blockchains usually have like scaling problems. Scaling is simply like the number of transactions that you can execute, or the execution time. It's pretty slow and pretty much wrongly scaled by Bitcoin, for instance. And there are many attempts how blockchains can be scaled better. Usually, if we speak of like blockchain scaling, The first thing that comes out, that's the blockchain scalability trilemma. Here we got like usually like three properties like securities, how secure is our blockchain in terms of like, I don't know, like stake or computational reward or mining or anything. The second property is decentralization, which means practically it's difficult. It's connected somehow to counterparty risk. So basically, we can say if there's a big decentralization in the network, then we don't really have like counterparty risk. Otherwise, we might as well have like I mean, if like all of your nodes of your blockchain are run by one company, then that's for sure like a counterparty risk. And we got scalability. For the first one, scalability is like the number of transactions per second and like the execution time of one transaction. And the blockchain scalability trilemma looks that way that so usually we say you can pick two properties from these three. Okay. So there are like very secure and decentralized networks like the Bitcoin protocol or Bitcoin network, which is not very scalable. Something similar was true like for the first versions of Ethereum as well. Or you got like other protocols which are like pretty scalable, pretty much decentralized, but perhaps not so secure. Usually what's mentioned is like, I don't know, Polygon might be one of this network. Again, I mean you can argue with me, but Polygon can be like a good pick. And we got like system which are secure and scalable, but not so much decentralized. It's like all of your consortium ledgers fell in this category. And so the question is how we can scale up blockchain. And we got like several directions. So for instance, we can scale on-chain. On-chain scaling means using kind of a better consensus algorithm or a new different, more scalable consensus algorithm. So like there's like innovation in this field as well. If you just pick like the SUI protocol, they have like this SNARK or the further implemented Narwhal and Tusk consensus algorithm, which works with like mempool decentralization with like a decentralized with like a directed acyclic graph. So it's a pretty cool innovation. It looks pretty much like a further developed pretty cool consensus algorithm at the moment. But we can pick like other ways as well for scaling directions. We can think of like sharding. Sharding means that one node just stores piece of the blockchain and not the whole blockchain. We can do something which is like side chains, like parachains. If you're familiar in Polkadot, you get like one big blockchain, which is the relay chain, and you get like application-specific blockchains, which are the parachains. So practically, if you implement like a gaming application, then you don't pick as a decentralized app on your blockchain, but practically you're just gonna implement a whole application-specific sub-blockchain, I would say, just for this gaming application, which makes things more scalable, faster, and so on and so forth. And of course, we can have like really like off-chain scaling. I mean, without blockchain, it's like layer 2 scaling. And one example is like the state channels. It's like the Lightning network with Bitcoin. And of course, we can have like rollups. And we're gonna cover actually rollups in the next slide. So let's try to speak about like rollups. So the idea is with rollups that we bring a transaction outside the blockchain and we execute the transaction outside the blockchain. Sometimes not even in a decentralized way. Sometimes just by one actor, which is like the sequencer or the rollup operator, and we import the result of the executed transaction back to the blockchain. Okay. So that's the idea of rollup. And we got two different rollups for the first one. The first one is the optimistic rollup. So again, the idea is that we just pick a transaction, or not just one transaction, but like a few hundreds or thousands or 10,000s of transactions. We just bring these transactions outside the blockchain, and we execute these transactions with like a centralized rollup operator. We can call it as a sequencer. And after executing these transactions, or even like few thousands or 10,000s of transactions, we bring actually the result of the transactions back to the blockchain, like the state, like the work state. So the question is, why is it a good thing? Why is it something similar? I mean, you might as well say, okay, I mean that sounds great, but if you just execute the transactions outside the blockchain, we got a pretty huge I mean, it's not decentralized on the one hand, but it's even a bigger problem that we got a pretty huge counterparty risk because the one actor that executes these transactions outside the blockchain can actually cheat, can actually do anything, and can actually import back to the blockchain anything, I would say. So how we can make sure that basically the imported result by the rollup operator or sequencer is correct in a sense. And for this one, one structure is the optimistic rollup. So in optimistic rollup, the rollup operator imports back the results into the blockchain. But the point is that we're gonna have here a challenge period. So it looks that way that these results on the blockchain that were imported back by the rollup operator are still not finalized. So they are still in kind of a temporary state. And then there's like a challenge period in this temporary state. So practically in this temporary state, practically everybody outside the blockchain can challenge these results, saying that, hey, I just executed the same transaction that the rollup operator or the sequencer, and I got a different result. And I can even prove it. Proof is something which is executed by smart contracts, so it can be done online. And if that happens, that basically that result by the rollup operator is not correct. So if it turns out that the rollup operator tried to cheat basically on the result, then basically this temporal state is basically rolled back, so it's not gonna be valid. And then usually there's like incentivization as well in terms of like slashing a stake, which demotivates basically rollup operators to behave in a wrong way. Okay, so basically here the idea is we got a challenge period for the results. There can be a fault proof. Fault proof can be done by independent validators. Fault proof is evaluated on the blockchain. And basically, if there's like a rollup operator is incentivized from a financial point of view to deliver correct results. That's done in a way that basically, if you want to be like a rollup operator, you need to put like a stake in the network. And if it turns out that you just tried to cheat the network, then stake is gonna be slashed. So practically lost, or half of the stake is lost, and so on and so forth. So, and basically, if there's like a fault proof, then again, this result by the operator is rolled back, and then the state is not finalized, and the rollup operator is badly slashed, I mean, or is slashed. So basically, there's a lose, there's a lose in terms of crypto money, and basically even the actor that created this fault proof gets like incentivized somehow. So that's basically the idea. But actually, the assumption is that due to this economical mechanism, actually, this is like kind of an economical guarantee. So due to this economical guarantee, people won't really try to cheat as a rollup operator because they are not motivated to cheat, basically. Okay. One such platform is Optimism, or Optimism was actually the first optimistic rollup. And then perhaps one thing, so I mean, this system works correctly, supposing or with the assumption that there's at least one one honest party that really tries to reevaluate proofs and then challenge and create fault proof during this challenge period. If that does not happen, then that can be like a problem. Okay, so that's like an optimistic rollup. And the other way of doing a rollup is like a zero knowledge rollup. It's practically, I mean, the idea is similar for the first run. We're not gonna execute the transaction on chain, but we just bring our transaction off chain, which is executed by a special party. We can call it as a rollup operator or a sequencer. And I mean, that can be not just one transaction, but usually like a few thousands or 10,000 transaction. And basically the execution result is brought back to the blockchain. And then basically for the execution result, there's a cryptographic proof that things were executed in a correct way. And this proof is realized by a zero knowledge proof. So practically pretty similar. So there's a zero knowledge proof that the rollup operator or sequencer executed our transaction in a correct way. And then this proof can be validated on chain by a smart contract. Okay, and then the result is gonna be valid only if the zero knowledge proof is basically valid as well. So there's like one smart contract that's, I mean the rollup operator can bring like data and zero knowledge proofs with the help of the smart contract. And then if the smart contract, the smart contract gonna evaluate the zero knowledge proof, and if that turns out to be valid, then the data will be accepted as the result of the off-chain execution practically. Okay, so that's like the idea for ZK rollup. Some comparisons between like optimistic and ZK rollups. So I mean they are. The core idea is similar. We gonna execute a transaction off chain by like even by one party, not even decentralized. Some of the core differences, nevertheless. I mean, what's important that in optimistic there's like an economical security guarantee. So basically, the stake is slashed. There's like an assumption that at least one honest party gonna react. So these are like economical security guarantees. And well, I would say like economical security guarantees are sometimes difficult. So we might as well, just assume like a situation that I'm a roll-up operator and I say, hey, I have a stake which is like 10 ether, and if I try to cheat, that's gonna be slashed. So practically I just lose this 10 ether. But and it sounds as like an incentivization mechanism not to cheat, but perhaps I am in a situation like I don't know, with like transaction reordering or kind of a minor excessive value setup that I could gain like I don't know 100 ether if I cheat. So basically, in such a situation, I might take the risk of cheating and actually losing the 10 ether. Even if I'm for the first run, it doesn't really make sense, but perhaps in like a more extended economical sense, it makes sense for me even to cheat. So again, like economical security guarantee is sometimes challenging, I would say. So disadvantage we got here like a long finality time. We need like one honest challenger. This long finality time against like 1 week, like with optimism, if I'm not mistaken. But there are some workarounds actually, like there are like the so-called liquidity bridges that try to somehow makes these things faster. Basically, they just provide like kind of an insurance for me, and then they just pay out for me right away, basically. So I don't need to wait like for the 1 week. So the other one is ZK rollup. There's like a cryptographic security guarantee. It's a fast finality. So basically, as I just put my results to the blockchain, it's gonna be either okay or not okay, but basically that's gonna be final right away. Of course, there are issues with like performance. So even if you say like, yes, so sometimes like in a SNARK, basically evaluating the proof is fast, but if we just consider blockchains and smart contracts, especially if you just consider like fast blockchains, having like block times in like, I don't know, seconds. So sometimes it's just challenging even to like create like a cryptographic, like a zero knowledge verification, process that runs in a block time of a pretty fast blockchain. So I would say, of course, ZK rollup looks much better for the first run, but of course there are like performance issues, and of course sometimes even just, I mean, generating the proof is not necessary efficient. So I mean, even in like generating the proof can be like challenging, and of course verification can be challenging as well. So let me take a look how we can like build up such a proof, just in a second. So to imagine how we can build up such a proof, basically, let me just imagine the situation that we want to execute like one transaction off chain, so out of the blockchain. So what we have here usually, we got here kind of a Merkle tree. We don't necessarily have like Merkle tree that's usually like more complex. We have like kind of a Patricia tree or sparse Merkle tree. It's a little bit like more complex, but it doesn't really matter. So we can have something, basically we can have accounts, like supposing we have like an account balance based systems. We can have basically accounts in our Merkle tree, and we can have transactions. Okay, again, these are not necessarily the blockchain transactions. I mean, they are certainly not executed in the blockchain, but they're gonna be executed off chain. And what we have here, so this is like a Merkle tree, like containing all of our accounts and balances that are basically off chain. And then we can imagine that basically we got somewhere the blockchain as well. Again, our off-chain accounts are not written into the blockchain, but basically we can have like a lot of off-chain accounts or roll-up accounts, and the Merkle tree of these accounts can be already written into the blockchain. So it gives us some kind of data consistency. So these are like accounts, like Alice has like, I don't know, 2 Bitcoin, Bob has like 3 Bitcoin, and these are stored basically outside the blockchain, totally off-chain, but basically they are organized into a special Merkle tree, and the root of the Merkle tree is in the blockchain already. Okay, and we can have transactions as well, and these are transactions for the roll-up. So these are like off-chain transaction that might be the same as an on-chain transaction, but that might be different as well, or a little bit different as well. So a transaction is something like send from to a certain amount of crypto or any kind of token, or even like one NFT token or something similar. So that's like a transaction. And what we do basically, so we will apply such transactions to this Merkle tree. And then if we apply it, we're gonna have like a new system, a new state system. So we can imagine basically that things look that way. I'm just having this one a little bit like, perhaps this, yeah, this picture is better. So what I'm having here, I'm having like accounts. We got like two sides of the picture. One is the blockchain, and the second one is, that's like the coordinator, that's like the roll-up coordinator or sequencer. So the idea is basically we got like accounts here on the roll-up, like Alice, Bob, Eve, Mallory, and so on and so forth. And these are like roll-up accounts, and we're gonna have like one transaction saying that, hey, Alice is gonna pay for Bob like, I don't know, one roll-up token, for instance. Okay, but that can be something which is like, like, I don't know, not Bitcoin, but like kind of a roll-up version of Ether or like USDC or USDT or something similar as well. And if we have the transaction, again, one thing is that basically the Merkle root of this whole balance structure is already written into the blockchain. And if we have this transaction, which again saying like Alice transfers to Bob something, what we can do, we can check the signature of this blockchain, of this transaction. We can actually check if Alice has like the enough amount of token or crypto to transfer to. And then we can create basically a new Merkle root and the new new Merkle tree. And the new Merkle tree, I mean, supposing that this transaction was correct, can contain already the modified balances. So it can contain like that Alice has like less token and Bob has like more token. Okay. And from this whole stuff, it's like, again, the old Merkle root is written into the blockchain. And we can basically create a zero-knowledge proof that we have a new Merkle root. And the new Merkle root is like the result of executing this transaction on this old Merkle tree. And then in this old transaction, basically, like Alice could create like a signature with her private key on this transaction, and then this transaction is like modifying the balance of Alice to Bob, I mean transferring tokens from Alice to Bob. And in the new tree, basically Alice has less balance and Bob has more balance. And basically, just let me just imagine this is like one big complex computation, and this one big complex computation can be expressed with zero-knowledge proof, like in Circum as well. And if you just imagine this as one big computation, we're gonna give like a zero-knowledge proof for this big computation. And we just gonna write the Merkle root into the blockchain with verifying this whole zero-knowledge proof. So basically, the Merkle root is written into the blockchain with the help of a smart contract, and we're gonna write in the new Merkle root into the blockchain only if there's like a zero knowledge proof beside the Merkle root as well. And this zero knowledge proof gonna prove this whole complex computation. Again, that there was an old Merkle tree, Bob had some balance, Alice had some balance, Bob had some balance. There was a transaction which like a private key signature, and this transaction just transferred a few tokens from Alice to Bob, and as a result, there's like a new Merkle tree with having like Alice more tokens and Bob less. Alice less tokens and Bob more tokens, and that's like a whole complex computation. And this is like with a new Merkle root and with a zero-knowledge proof, we're gonna register this to the blockchain. Okay, so that's like an off-chain transaction. And basically, let me just check if I just forget something. So there's a transaction sent from to an amount, or if that's not an amount, if that's not a fungible token, that might be an NFT as well. So we're gonna check if from and to are on the account tree. So on the Merkle tree, basically these are the old leaves of the Merkle tree. So the old Merkle root should be already in the blockchain. We're gonna check if the from has enough balance. So we're gonna just debit as a computation the from account with the amount. We're gonna credit the to account with the amount. We're gonna calculate a new account tree and the Merkle root for it, and we're gonna create a zero-knowledge proof about the calculation, and we're gonna publish the new root and the zero-knowledge proof to the ledger. And again, on the ledger, there's like a smart contract that practically validates that zero-knowledge proof. And if the proof is valid, we just record the new root to the ledger. Okay, so that's like the technical basis for executing off-chain transactions in a rollup. And of course, so I mean, one question, we can imagine that this rollup is like a centralized operator. So the centralized operator cannot really cheat, like in a sense of like, cannot cheat really the transactions. But what the centralized operator can actually do, the centralized operator can disappear. So basically, all of these transactions and all of these state balances are stored somewhere as well. And there are two options of doing this. I mean, they are stored because if the centralized rollup operator vanishes or just disappears or just shuts down, then things can be messy unless everything is stored somewhere on a decentralized storage. And there are two ways of storing basically all information. One way of doing is it's like storing on a decentralized storage. Another way is like storing all of this information in a blockchain in special fields. So for instance, like in Ethereum, you can store like information without much cost in the call data, which is like the logs practically in the blockchain. And there's like there's in Ethereum like the blob storage as well, where you can like store temporary information. So again, there's like a ZK verification, but I mean, despite the fact that everything is hardened or practically proved by zero knowledge proofs, this whole information is stored as well somewhere, because otherwise there might be like, some attacks, not again the correctness of the execution of the proof, but like if the rollup operator disappears, then it can be difficult to replace this single rollup operator with another one unless all of the information is stored somewhere publicly, like in a decentralized storage or in special blockchain fields. Okay, so that's like one off-chain transaction. And then based on this one off-chain transaction, we can basically like build up something more complex. So the general idea is that we got two parts of the system. We got the blockchain and we got the rollup, or that's like the rollup coordinator. And basically, it's just we don't have like just one transaction or one batch or blocks or off-chain blocks, but we can have like several transactions. They are executed or they are implemented with the same logic. So we got one Merkle tree with accounts and balances, and we can have like actually not just one transaction here, but several transactions. And if you just execute several transactions off chain, then we're gonna get like new accounts and balances. And again, we just write the Merkle root of these new accounts and balances with this whole validity computation into the blockchain. So practically there's like one zero knowledge proof on the execution of all of these transactions as well. And we can imagine that we can have one more step or even several more steps. Like we can have some new transactions. Again, these are like roll-up transactions, not necessary blockchain transactions. I mean, they can be similar to blockchain transactions from a structural point of view, but they are executed off chain. But anyway, we're gonna have like a few other roll-up transactions here. So we just create the new accounts and balances, and we just create a new Merkle root on it, and we just write into the ledger the Merkle root of the transactions if we can provide a valid zero knowledge proof that basically all of these transactions were executed in a correct way. Okay, so that's like the idea of like executing a lot of transactions off chain. And usually we got like two more integration points. So basically we have like a smart contract, how we can bring like elements from the blockchain to the rollup system. Uh, it depends actually what we want to bring outside the blockchain. If it's like kind of a token, we can imagine that we just burn this token in a smart contract, and there's like kind of an integration similar to a bridge, which makes sure that if we burn this token on the blockchain, then on the rollup we're gonna create practically the same token or a similar token. And we can imagine one such similar mechanism actually outside the blockchain, which is like a withdraw. Uh, Again, if it's tokens, then basically we can imagine that we just burn the balance, burn the token somehow on the rollup, and we just have like a smart contract integration. And the smart contract integration gonna just create or mint our new token practically on the blockchain. So again, these are like direct integrations, how we can bring out information from the blockchain to the rollup coordinator and withdraw information from the rollup coordinator to the blockchain. Usually it's a little bit questionable what we have here in the rollup. So the easiest way, if you just use like tokens, like fungible or non-fungible tokens, these are like easy things, but basically things are usually more complicated and of course more useful. We might not as well have like here like just tokens, but there are implementations of like the Ethereum virtual machine off chain. So basically, the idea can be that basically we can execute everything what we have on like Ethereum on a rollup coordinator. It's because like the whole Ethereum virtual machine running in a Zk EVM, zero-knowledge Ethereum virtual machine style, and basically any kind of Solidity program that can be run on an Ethereum or Ethereum style blockchain can be actually brought out to a rollup coordinator and executed off chain. And then if it's fully general purpose, it's more questionable how this two integration, which is like a token, it's like a deposit and withdraw, look like. It can be more complicated, but it's just solvable. Okay, so that's the zero knowledge roll up on a high level. And I got one more slide, which is like might be interesting or might be pretty new. So we got something which is like a hybrid proof. So we spoke about like optimistic and zero knowledge rollups as a two ways of creating a rollup, but there's like a hybrid approach as well. And in a hybrid approach, we just combine optimistic and ZK rollups, and we do it with an naysayer proof. So the idea is for an naysayer proof is that we practically combine this the zero knowledge and the so-called fraud proofs from optimistic rollups. So let me just imagine the situation that we want to create like a zero knowledge rollup. So we just put our execution off chain, we execute it off chain, and we just bring back the data to the blockchain with a zero knowledge proof. But let's just imagine the situation that either our zero-knowledge proof is pretty big or our blockchain is not too performant, so it's pretty slow and can execute just a few steps, so might not be capable of like validating even a zero-knowledge proof. So in this sense, we can say that, hey, we're just gonna bring back the zero-knowledge proof on chain, but we not validate actually the zero-knowledge proof on chain. It's because we just cannot do it because it's just too performance intensive. So instead, what we can do, we can just leave our practically results and our zero-knowledge proof on chain, and we're gonna have like a challenge period. We don't like finalize our data on chain, but basically our data and zero knowledge proof will be on chain in a temporary state, practically without being finalized in a challenge period. And in this challenge period, practically everybody can challenge our results from outside the blockchain, saying that, hey, that zero knowledge proof is not valid for some reason. And again, it's like a combination of ZK and optimistic rollups. It can be used in system where the on-chain executional possibilities is very, very limited. And actually, there's like one good example for that. It's like the Bitcoin blockchain. So in Bitcoin blockchain, you have like a very limited possibility to program on chain. That's like the script language, which is like not even Turing complete. So basically, like as far as I know, theoretically there could be possible to like verify a zero knowledge proof on the Bitcoin blockchain as well, but it would take like, I don't know, like 1 GB block size or something similar, and I don't know how many hours. So practically it's not possible, but with some clever tricks combining like zero knowledge proofs and challenge periods basically used in optimistic rollups, there can be something similar implemented. So as far as I know, there's like initiatives as well implementing naysayer proofs in like the Bitcoin virtual machine as well, which is like an off-chain virtual machine computing or bringing somehow the smart contract possibility or more general smart contract possibility to the Bitcoin network. So that was actually my presentation. This was like a pretty, I mean, I wouldn't say theoretical, but it was like a more like presentation intensive session or meetup, even from myself. I did not create like anything to show in terms of code. But that's gonna be like the challenge, the developer challenge. Just try to create a very simple ZK proof in Circum or Noir. Sorry, it's not a ZK proof. It's a very simple rollup. I'm just correcting the slides. Create a very simple rollup in Circum or Noir. It's not even necessary to create like a full scale rollup. You can do like one transaction that is somehow, so I mean something similar. Just create some old Merkle roots, one transaction, and just create a new Merkle root for like one kind of a special token. That should be enough. That's not like a full full roll up. It's just kind of an off-chain transaction execution. But actually this is like pretty much part of all of the ZK rollups. So that's the developer challenge again. Not creating a simple ZK proof, but creating like a very simple off-chain transaction or roll up in Circum or in Noir. So we got some links and resources, and then basically I would say in one or two of these resources you might as well find something which is like a simple tutorial how you can create like a very simple off-chain transactions with like Circum. So you might as well take a look actually. And I would say that was for today. We got like 5 more minutes. So if you have like any questions, I can try to answer them. In the meantime, I'm just reading the notes in the chat. So basically, usually the question is, we're gonna share. I mean, it is live streaming YouTube. We're gonna share the slides. We're gonna share the GitHub repo. So basically, you will find everything, even the recording as well, even the slides as well. And well, basically, if you just don't manage like having like a simple repo for like a very simple, I mean, if you don't manage the developer challenge, I'm gonna implement like a solution for a development challenge like in a month as well. So that's something that you're gonna find basically in the repo as well. So there's like YouTube live stream. So on slide 11, there's a question: finality time for any transaction, the finality time for the Merkle root. So basically, I mean here the finality time. Yeah, the finality time is basically, I mean, it depends on two things. So basically, just imagine that we got here the Merkle root, and the Merkle root is a smart contract on the blockchain. And then, so basically, finality looks that way. I mean, the time of this transaction, well, it doesn't matter. As fast you can basically compute your transaction. Usually, it looks that way that you don't have just one transaction, but like several transactions. And the idea is that here on the blockchain, you have like one smart contract. So basically, the time of like such a rollup execution should be at least one block, but it can like span several blocks as well. And if you just write back like information to the blockchain, again, just imagine a smart contract having two inputs. One input is like the numerical root, and the second one is the zero knowledge proof. And basically, what the smart contract is gonna do, checks the zero knowledge proof. If the zero knowledge proof valid, it accepts the Merkle root. And then basically in the zero knowledge proof, you find the calculation of the Merkle root as well. So basically, the zero knowledge proof, the mathematics and the on-chain smart contract verification gonna guarantee for you that the rollup cannot post like false things. Basically, if it posts like a false zero knowledge proof, or if it posts like a false Merkle root with like a valid zero knowledge proof, but for something totally different, the smart contract are gonna recognize it, and then it says that, hey, that's not valid. That's not gonna be a new word state. That's not gonna be a new Merkle proof. So basically, mathematics guarantee for you here the consistency. Okay, I mean, certainly this is like from a cryptographic sense, it can be like pretty difficult. So basically, we got here mathematics. And then there are like exceptions how you can cheat. For instance, depending on your zero knowledge proof, if you have like quantum computers, and if your Z-key algorithm is not quantum resistance, you might as well able to cheat and just publish false proofs. So there are like exceptions, but again, this is like a cryptographic guarantee, and the cryptographic guarantee is usually regarded as stronger than like an economic guarantee. Okay, so are there any more questions? We got like, I don't know, 1 or 2 minutes, 2 more minutes. So if there are no more questions, I would say that was for today. Probably we're gonna have like one small session in December, wrapping up everything and just relaunching basically the new session. And then yeah, so if you have just one quick question, we got like 1 minute, then just go ahead. I'm gonna try to answer. Anyway, you can basically use like the Linux Foundation decentralized trust Discord channels as well. I'm gonna try to answer questions here as well. Yeah, so the question is if there's like any ZK rollups using STARKs instead of SNARKs. STARK is scalable, transparent argument of knowledge. Uh, Honestly, I don't know, but the point is usually it's not so typical to use STARKs in rollups. It's because STARKs create bigger proof that are slower to verify. So STARKs are not so practical for on-chain verification. And then basically you need like a fast verification and small data side for blockchain verification. It's because you can do it like in a smart contract, and a smart contract has limited like resources for computation, and you don't want to like like store a lot of information in the blockchain. It's because like in a blockchain a few kilobytes is already big data. So there might be like Stark implementation, but it's just not so typical because again, Starks create like bigger proofs that are slower to verify. And then you got limited resources in terms of computation in smart contract. And then well, you want to store as few information on chain as possible. So that's like the short answer. So I would say that was for today. If you have any more questions, just feel free to chat me here. I'm gonna try to answer them as fast as possible. So thank you very much for your attention, and then yeah, let me just meet in December.
Sounds good. Thanks, Daniel. Thanks, everyone. And I see the question, will the recording be on YouTube or Discord? I think both. I mean, it will be on YouTube. It is on the LFTT YouTube right now, and I think Daniel will share the link. So, all right. Thanks, y'all.